Welcome to the course Business Analytics and Data Mining Modeling using R. So, in the previous lecture we concluded our discussion on multiple linear regression. So, in this particular lecture we are going to start our discussion on the next technique, k nearest neighbors. So, this particular technique is more of a machine learning algorithm, a data mining technique. The previous one, the multiple linear regression, was the statistical technique. So, let us start our discussion on k nearest neighbors or KNN. So, as we have been discussing in previous lectures about the difference between statistical techniques and data mining techniques, that in one specific difference being that in statistical techniques we assume some form of relationship between the outcome variable of interest and the set of predictors. For example, in linear regression, multiple linear regression and other regression models, typically we assume that there is a linear relationship between the outcome variable of interest and set of predictors. However, in data mining techniques, as we have often mentioned, that no such assumptions about the form of relationship between outcome variable of interest or set of predictors are made. So, therefore, very first point in KNN also that we have specified in this particular slide is that no assumptions about the form of relationship between outcome variable and the set of predictors. Now, another important fact about KNN and typically about other data mining techniques as well, that non-parametric method. So, KNN is specifically non-parametric method. So, for example, in the multiple linear regression that we concluded in previous lectures, we used to estimate the betas and the sigma value, right. So, those we do not have such parameters to estimate. So, no parameters from the assumed functional form. So, those betas were coming from the linear relationships that we had assumed about the outcome variable and the predictors. So, those betas were required to estimate, right. So, no such parameters, especially from the this functional form point, from the functional form sense are there to be estimated, right. So, this is being non-parametric method. Then how do we build a model, what the model is about, right, what we actually do in KNN modeling. So, what we actually do is we learn from the data. So, useful information from modeling is extracted using the similarities between the records based on predictors values. So, each row representing the records, each row in the data set will represent a record, and the different than the values of predictors for each record, and for different records we can find out the similarities between those records, and those similarities would become the basis of our modeling exercise. So, typically how do we find out, how do we measure the similarities between records? So, typically distance based similarity measures are used. So, let us move forward. So, as we said, we learn from the data, even though we learn from the data itself using statistical techniques as well, but we assume about assume about the structure of the data or the relationship between variables, right. Here we do not have such assumptions. So, let us discuss few more things. For example, we talked about the similarity between records, and specifically the distance based matrix, distance based similarity matrix are used. So, one of the popular metric that is used for distance is the Euclidean distance. So, for two records which are having values of predictors as denoted by x1, x2, xp, if there are p predictors, and the second record being w1, w2 and wp. So, the distance between these two records, as we all understand the Euclidean distance formula, d EU is going to be square root of x1 minus w1 square plus x2 minus w2 square and plus up to xp minus wp square. So this is going to be the this is the typical Euclidean distance formula that can actually be used to compute the distance and therefore the distance based similarity. So the main idea being that using the predictors information as the coordinates, right, for a particular record, and therefore for two records to be considered as similar or considered to be closer, if the distance is smaller, distance of values, predictors values between those two records are smaller, then probably we can say that those two records are similar or closer. So this particular distance based metric, Euclidean distance metric, is quite popular in KNN. The main reason being low computation cost as compared to other distance metric. Some of other distance metrics that could be used are statistical distance or Mahalanobis distance, Manhattan distance. So there are some other metrics also which can also be used. So some of these other metrics we would be covering in other discussions about discussions about other techniques, other data mining techniques and statistical techniques. So KNN Euclidean distance is the most popular metric, as we said, especially for the reason being that low computation cost. Now the main reason, another reason is that we need to compute more distances in KNN, and therefore we would prefer a metric which is computationally less computationally intensive. As expressed in this last line in this particular slide, Euclidean distance is preferred in KNN due to many distance computations that we have to perform. Now another important aspect of KNN is the scaling of predictors. So as we talked about the distance metric that are going to be used. So because of this the predictors, set of predictors, different predictors having different scales, different units, and because of that because of just the scale, some of the predictors might dominate the distance, because if you look at the Euclidean distance formula, it's just the way it is being computed, the difference between predictors values of 2 points, right. So therefore the particular difference of a predictor which is having higher scale might dominate the overall distance value, and therefore might dominate the results. So therefore scaling is very important in KNN. So therefore before we start our KNN steps, it is advisable to standardize values of predictors. So how do we apply KNN in a classification task? So main idea is to find k records in the training partition. So again here also we would be doing that partitioning, training, validation and test partitioning, and the training partitions, the records belonging to the training partition, would then be used to find k records which are neighboring the new observation to be classified. So the new observation could be in the validation partition, or if we have the third partition, the test partition, then this new observation could be, or it could be a completely new observation as well. So new observation could be in the validation partition or test partition, and we need to find the k records from the training partition which are closer to this, which are neighboring to this new observation, closer to this observation or similar to this observation, or neighboring this new observation. Now these k neighbors are then used to classify the new observation, right, into a class. So typically the predominant class among the neighbors, that is generally assigned as the class of new observation, right. So these are the two main steps for KNN, especially for the classification task. So let's move forward. Now the next important point would be finding neighbors and then performing this classification. So, if we look at a few steps for this for the same, first we need to compute the distance between the new observation and training partition records. So, that is why when we talked about why Euclidean distance metric would be preferred in is generally preferred in K-NN technique, K nearest neighbor technique. The main reason being, as expressed in the first point, we need to compute the distance between the new observation that we want to classify, the new record that we want to classify, and the training partition records. So, if we have a large number of observations in our sample, and therefore large number of observation in our training partitions. So, the number of distance computations that we will have to perform would be much more in comparison to other scenarios. Therefore, other distance matrix that we talked about, the statistical distance or also called Mahalanobis distance, and we also mentioned one more name, Manhattan distance. So, those matrices are not actually used. Then once the computation, once the distance between the new observation and the training partition records, once the distance has been computed, then we can go ahead with the point number 2, that is to determine K nearest or closest records to the new observation. So, out of all the records in the training partition, and right, so the distances have been computed for all of them. So, out of all those distance values, we can find out the K nearest or K closest records to the new observation. Now, within these, now this will also, so the next step would also be that find most prevalent class among K neighbors. So, once K neighbors have been identified in step number 2, we can find out the most prevalent class among K neighbors, and once this is done, this particular class, the class most prevalent, the majority rule decision would take place here. So, the among all K neighbors, the class which is more common, which is the majority class among those K neighbors, that would be the predicted class of new observation. So, that is the typical procedure, typical steps that we apply in K-NN modeling for classification tasks. So, let us understand some of these concepts using an exercise in R. So, let us open R Studio. So, first as first step, as we generally do typically do that, first we need to load this particular library XLSX, so that we are able to import the data sets available in Excel file. So, the data set that we are going to use here is the sedancar.xls file, the sedancar data set. So, let us look at the data set first. So, this is the one. So, this particular data set we have used in previous lectures as well. So, in this particular data set we have 3 variables, mainly annual income and household area and ownership. Annual income and household area being the numerical variable, and ownership being the categorical variable. So, for our classification task that we shall be performing, ownership would be the categorical outcome variable. So, we would be using the 2 variables annual income and household area to classify the ownership of a particular ownership of observation, right. So, for 2 different classes are there, non-owner or owner. So, whether a particular household, so a unit of analysis here is the household. So, for different households we have the information about those household as annual income of those households and the area of those households, and then whether they own sedan car or not. So, typically we would expect that the households which are having higher annual income, they are expected to own a sedan car. Similarly, household which have bigger, which have larger household area, they are also expected to own a sedan car, because you would need more space in your household to park to make the parking arrangement of your car. So these two variables, numerical variables, are going to be used to classify or to build our model, KNN model, specifically classifier model. So let's import this data set. So the function, once we have loaded the library, this xlsx, the read.xls function would be available for us. So we can call this function, and as we have been doing in the previous lecture, the file.choose function would allow us to browse this particular Excel file. Other ways of importing or mentioning this particular file that we have discussed in the supplementary lectures as well, that you can mention the absolute path of the file name, or you can change your working directory using the setwd function. And then once that is done, and if your file, the Excel file, has been copied or stored in that working directory, then you can use the name of that particular file, that is siddhanka.xlsx, in the first argument, and it would be easily imported. So different ways of importing a particular file. So let's execute this code. And you can see in the environment section we have imported the data set. So this has been stored in, we have used the data frame df, and then 20 observation of 3 variables. If you want to confirm the data that we had in the Excel file, you can just click on this icon. This is a small icon that appears in the environment section, and then the data subsection. This is a small worksheet kind of icon. So you can immediately see this, that the annual income household area. Immediately you would be able to view this particular file and this particular information. You see, another important aspect about this R environment or R studio environment is that once we import a particular data set, it would be loaded into memory, and therefore immediately whenever we click on this particular small icon, or whenever we want to access the full data or few observation or few rows, the output is produced quite quickly in comparison to when we open the Excel file. It takes a bit more processing and takes a bit more time for especially for larger Excel file to load, and therefore that being the main difference. So once we import, the data set is loaded into memory, and therefore it can be easily accessed in a much faster or quicker way. So the next line is about deleting the removing the NA columns. So once we have data set in Excel files, and if we happen to delete some of the irrelevant columns in those Excel files, so those deleted columns would be picked up as variables, NA variables, variables having NA values in our environment. So therefore if we had such columns in the imported data set, we will have something like 20 observation of 5 variables if we had 2 columns which were deleted, irrelevant columns which were deleted in the Excel file. So to get rid of those situations, we have this next line where as you can see in the column value, so for the data frame, as we have talked about in the supplementary lectures, that the first one is in the brackets, within the brackets, first value is for the rows and the second value is for the columns, and within the second for the second value we are applying this apply function, where we are applying this is.na function, whether and then the second argument is the margin 2. So that means that the function that is all specified in the third argument is going to be applied column wise on different variables of this particular data frame, right. So if data frame is having NA values, so that would be appropriately returned, and then those columns would be appropriately subsetted using this brackets. So let's get rid of these NA columns. Now let's look at the structure. of this particular data set. So as you can see, using the str function, the structure function, we get to know about these three variables: annual income and household area, being two numerical variables, then the ownership, the categorical variable or factor variable as it is called in our environment, with two labels, non-owner and owner. Now let's look at the first 6 observations. So this is how it is. Now one of the first few things that we do in R is in our modeling exercise, that we plot, we generate a scatter plot between the predictors or important variables of the model. So in this particular case, we have two variables, annual income and household area, and you would see that the ranges have been appropriately specified, as we have been using this particular data set in previous lectures as well. So let's generate this scatter plot. Let's also generate the legend for the same. So these are the points. So this different characters are being used to denote the owner or non-owner class among these points. So on x-axis we have annual income and on y-axis we have household area. So we would like to classify these observations into belonging owner or non-owner category. As we can see, this is particularly small data set. Already we can see a clear class separation between these points. However, we would like to do same the classification task using a modeling. So for example, if we have a new observation, let's say annual income 6 LPA, this is the new observation. A particular household having annual income as 6 LPA and household area as 20,000 the square feet, right, 22,000 square feet, because we have the household area in the hundreds of square feet. So this observation, if we would like to let's also plot this observation using the point function. So point function can actually be used to plot points or add points in an existing plot, the current plot. So you can see the type is the argument that we are specifying. So it's P, right. So and the plotting character is also being selected differently, different plotting character has been selected. So this point would be added into the existing plot. The idea is that to understand that we want to classify, this is the new observation. So this particular observation we want to apply KNN, and we would like to classify it into one of the two classes, owner or non-owner. Now as we have discussed that scaling is an important aspect of modeling using KNN, because the scales, different scales that could be there for different predictors, and that could actually, so some of those predictors having higher scale could actually dominate the distance matrix that we are going to use, the Euclidean distance matrix that we use. So therefore they can dominate the results and then influence the results, and we would end up end up with the meaningless classifications. So let's before proceeding further, let's normalize the values, standardize the values. So let's take a backup of this particular data set. Now as you can see, we have selected just two columns for annual income and household area, column 1 and 2, and because these being the numerical variables, so the scaling is to be applied on only these two variables. So you can see we are using a scale function. So scale function can be used to apply different kind of scaling. So for example, in this particular case, the first argument is the variables as subsetted using this from this data frame, right. So we would be applying scaling on these variables, two variables, and then you would see the second argument is about the centralization of these values, so which has been specified as true. Then the scaling of these values, which has been specified as true. So centralization and scaling both would be performed using this particular function. If you are interested in finding out more information on this particular function, you can type scale in the help section, and you will get more information on this particular function. You can see scale is used for scaling and centering of matrix like objects. So scale is generic function, and whose default method centers and or scales the columns of a numeric matrix. Right, you can see center either a logical value or a numeric vector of length equal to the number of columns of X. So different types of standardization or normalization scaling could actually be performed using this function. In the coming lectures, we would be trying different variations of the same. So let's perform this scaling here. Let's execute this code. Now let's look at the first 6 observations. As you can see, after the scaling has been applied, the values have changed, right. So these values have changed. So earlier the scale was different, now the scaling has been done, so that to eliminate the influence of the same. Now let's do the partitioning. So the data set that we have is mainly for the illustration purpose, and we are having very small data set. So therefore the results might not be that stable, therefore it is generally recommended to have a larger data set, and the data mining modeling is actually applied on larger data set. The process is suitable for the larger data set, where we can create partitions having enough number of observations, so that the results could be stable, right, and could be reliable. So in this case, because this is for the illustration purpose, we are going to partition this particular data set. We have 20 observations, 20 values. Now 15 values are going to be used in the training partition, and the 5 values, 5 records are going to be used in the test partitions. So partitioning, let's do the partitioning here. And then let's create the training partition using the index that we have just generated. So let's create this, the test partition. As we have been talking about in the previous lecture also, sample function can be used to create the indices, can actually allow you to select the random indices belonging to different observations, or different observation in your sample. In this case, you can see that second argument is specified as 15, because we want to draw 15 indexes. We want to randomly select 15 indices to create the partition, right. Replacement is also, so this process is done without replacement. So the first partition, that is the training partition, so all these 15 indices and the appropriate subsetting of the data frame DF is performed. In the second partition, that is test partition, the remaining 5 observation of the 20 total, that would be left for the testing partition. Now once this partitioning has been done, we can start with our modeling process. So as you can see, library class is actually used to perform the K-NN modeling. So let's load this particular library, and we'll do there is another important aspect of K-NN is the value of K. Till now we have been using a K as our reference, but K actually signifies the number of neighbors, number of neighboring values that are going to be used to perform computations, right. So we'll start with an example of 4 and n, that means the value of K is being taken as 4. But later on we will see how the appropriate value of K, optimal value of K can be selected, right. So let's execute this code. So the next function that we are going to use for K-NN modeling is the K-NN function. So wherein the first argument is the training data set, the training partition, so that we have appropriately specified. The second argument is the test partition, so that we have again specified. You can see only the numerical variables are being used, and then because this is a classification task, you can see the third argument, that is CL. So there we are specifying the different classification, different using the third variable in the training partition, that is ownership. So, from this using this argument, the classification would be used by the K-NN model. Now, we have also specified the value of k as 4. So, let us execute this particular code and we would see, let us execute run the summary function, and in summary you would see that out of 5 observations that we had in the test partition, right. So, 3 have been classified as non-owner and 2 have been classified as owner. If we are interested in looking at the classification matrix, we can use this table function. So, in the table function, first argument is always about the actual values, and then the second argument is for the predicted values, right. So, let us use this. So, you can see all the values have been the model that we build and the classification that we have got, as we can see from the classification matrix. All 3 owners have been all 3 non-owners have been correctly classified as non-owners, and 2 owners have been correctly classified as owner. So, if we look at the misclassification error, so this we can compute using the mean function, where we are equating the actual values with the predicted values. If anything is not equal, so that would be counted and an average would be taken, right. So, that will get the misclassification error. So, we would see that misclassification error in this case is 0. So, as because this was a small data set, so the results that we have they depend on the partition that we do, the observation that are selected in the training partition and the observation that are left over for the testing partition. So, in this particular case, we got the 100% accuracy and 0% error, but if you repeat the exercise, if you again do the partitioning, because this being a small data set, the results might change significantly. However, as we have discussed in the previous lectures, a larger data set is generally recommended, so that our results remain stable even if we repeat the exercise. So, we will stop here, and in the next session we will start our discussion on how to select a suitable or appropriate and optimal value of k for the K-NN modeling. Thank you.